Welcome to section 3.1. This is the first video you're watching in Algebra 2B, and we're going to talk about finding the intersection of lines, and we call them systems of equations. And so a system of equation is just multiple equations that you're asked to find where those lines intersect. So let's start with a few definitions, and for today we're only going to do the front side, and then tomorrow we'll do the back side. Okay, so for the front, take a look at the term consistent. It's the system that has at least one solution. At least one solution. Okay, so basically what it means is that the lines intersect at least once. So at this point in time, if you want to put a little note, basically the lines have to intersect. If the lines intersect, then we consider the system to be called consistent. And what we're going to do as we find these systems is we're going to actually then label them once we're done with the problem. So I'll show you that. Independent means that the system is consistent. So it's a consistent system that has one solution. And I'm going to underline that. That has one solution. And that means the two lines have to intersect only once. And so picture-wise, because a lot of us are visual, let's take a look at what it would be in a picture form. If I draw my graph, let's say, let me change colors so you guys can see the two lines. If I look at, here's one line, and maybe here's another, you can see that they intersect. They intersect once, and that means that anytime I graph two lines that intersect once, I would label this system consistent because it has an intersection, and independent because it intersects once. And I just want you to have a picture form so as you're going through you can see that. Okay, let's look at dependent. A dependent system is a system that is also consistent. And again, that means that the lines will intersect. That has infinitely many. Infinitely many solutions. And I'm going to underline that also. What that means in terms of a picture, okay, is if I draw my graph, I'm going to change colors again so you can kind of see my picture. When I look and I graph the first line, let's say the first line looks like this, okay? When I graph the second line, I end up graphing exactly the same line. And that means that they have infinitely many solutions because every point along that line is a solution of both equations. And so basically, as you look at this, you want to keep in mind that the lines are the same. Okay? So that's one thing. So if we see the line and we basically are graphing the same line on top of each other, we would label this system as consistent and dependent. And basically, if the lines are going to intersect, you're going to have two classifications. It's always going to say consistent, and then you're going to have to tell me, does it intersect once? That means it's independent. Or does it intersect all the time? That means it's dependent. Okay? The last definition that we want to know is inconsistent. And this means that the system has no solutions. Okay, so it has no solutions. So in terms of a graph, because I like to have that picture form there also, let me change my color. Let's go green this time. What it says is when I draw the first line, there is no intersection with the second line. They don't touch at all. And for that to happen, we know in geometry that the lines then have to be parallel. So these two then are parallel lines if they're inconsistent. Now, if you say the system is inconsistent, it only needs that one classification. You only have to say inconsistent, and you just go about your business. But if you say that they intersect, then you have to have two. Consistent and something, whether it's independent or dependent. Okay? And I like having the pictures there too so that you can look back and say, oh, that's what I'm supposed to say. Okay? Now here's what we're going to do. In the middle section, we're actually going to graph the two lines and find the point where they intersect. In order to graph lines, if we remember from part A, we have to have it in slope-intercept form, which is what we have for the first one. So I'm just going to rewrite this a second because I want to point out some of the things we learned in part A. We know that this value at the end, the B, is the same thing as our y-intercept, which means on the y-axis, I go down to -3, so -1, 2, 3, and I start my graph there. The 2 we write as 2 over 1, and that's my slope. And that tells us rise over run. Since the 2 is positive, we go up 2. Since the 1 is positive, we go right 1. So from that -3, we go up 2 over 1, plot a point. And then we go up 2 over 1, plot a point, up 2 over 1, plot a point, and we want to plot as many as we can. Now you'll notice I can probably get one more on the left side. So from that -3, instead of going up and right, I'm going to go down 2 and left 1. And what if I were you, I'd use your ID and kind of trace that, and you get a line. Now, most teachers in Algebra 2A said you only need a couple of points to make your line. In Part B, we want to have as many points as possible because I don't know where it's going to intersect my other graph. So I need to have both. Okay? Now, the second one, the problem is the equation is not in y equals form. So 3x plus y equals 7. So I need to make it where y is by itself to be able to graph it. In order to do that, I need to move the 3x to the other side. Since the 3x is positive, I'm going to subtract 3x, and I get y equals -3x, and then my 7 was positive, so plus 7. Now, as I look at this, I know that the 7 is where I start. The problem is my graph only goes up to 5, so I'm going to extend this a little bit and say, okay, here's 6, here's 7. So there's where I'm going to start. Now, normally on their graphs for tonight, you're going to get a 10 by 10 grid, so you're going to have enough space to do this. Okay? The -3 is really over 1, which says go down 3 and right 1. So from 7, I go 6, 5, 4 over 1. Down 1, 2, 3 over 1. 1, 2, 3 over 1. Down 1, 2, 3 over 1. And obviously, I think as of right now, you can see where the two lines intersect. So I draw my line and I extend it with arrows. And you can see that this is my point of intersection, and we label it as a point. This is over 2 up 1, so the point 2, 1. This is my solution. And again, every answer basically from now until the end of this chapter will be written as a point. I want to label now my system. Since it intersects, I know my system is consistent. And because it intersects once, if I look here, I know it intersects once, which means independent. So your answer is going to consist of two things. One is going to be the point of intersection, and 2 is going to be labeling what type of system you have. Okay? So there's the first example. Let's try one that's a little bit harder because there's nothing that says y equals. So let's start with the first one. X plus y equals 6. All right. I need to solve for y, so I'm going to move the x over. It's like a 1 in front, so I'm going to subtract a 1x. So y equals -1x plus 6 because the 6 is positive. Now, I don't throw the 1 in there normally, but I'm going to put it in today so we can kind of see what's going on. That says start at 6. So I'm going to extend this a little bit. Start at 6 and go down 1 over 1. If I write this, right, down 1 to the right 1. So down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. And I can see that this is going to get extended out in both directions. Okay. My second one, and I like changing colors so that you guys can kind of see the difference. My second one, let's go through. Negative 2x minus 2y equals negative 12. Okay. We're first going to start by moving the x. So it's negative, so to move a negative, we add it. I get negative 2y equals positive 2x, and then it was a negative 12, so minus 12. I divide every number by negative 2, and I get y equals, well, 2 divided by negative 2 is negative 1x. Negative 12 divided by negative 2 is a positive 6. Hey, I want to show you something. Take a look. We already did that graph. So we've already looked at this line. Therefore, we need to talk about the number of solutions. In this case, there are infinitely many solutions. Infinitely many solutions. Okay, because every point on that line is a solution. And then if I actually want to label my system, there are solutions, so we say it's consistent, and there are infinitely many solutions, so I look at my list on the left, that means dependent. Okay, so this is a consistent and dependent solution, and that means that there are infinitely many answers. Okay, so we tried to give you a couple of different types here. The one thing we are going to push this chapter is story problems also. And so I want to give you an idea of one of the story problems so that we can kind of talk about that. And I like this one because there are some fractions and decimals in here, which is real life. So I want to show you how to go about that. So I'm going to move over to the last idea. I'm going to change my color back to something darker a minute. Okay, here's what we're saying. On Ice Cream Shop, one customer pays $9 for 2 sundaes and 2 milkshakes. So we're talking about sundaes and milkshakes, and I'm going to read them in order. I'm going to call my sundaes X and my milkshakes Y. So that equation right there says I can do 2x plus 2y, so 2 sundaes plus 2 milkshakes, and that equals a total of $9. Okay? Another customer pays $13 for 2 sundaes, and we said sundaes was X, and 4 milkshakes, which is Y. Now I'm going to write them a little right next to each other so I can solve them. So I have 2 sundaes plus 4 milkshakes equals $13. Now, our job is to be able to solve these, to put these on a graph and figure out how much does a sundae and how much does a milkshake cost. So what is X and what is Y? Okay, so let's start with the first one. I'm going to subtract 2x so that I can get y by itself. So I have 2y equals negative 2x plus 9, because 9 is positive. I then have to get rid of the 2 in front of the y, so I divide by 2 on each of these. Y equals, well, negative 2 divided by 2 is negative 1. And I'm going to put over 1 because we're going to need that fraction anyways. Plus 9 divided by 2, I'm going to write it as a decimal here, 4.5. Now, normally I wouldn't suggest writing things as decimals, but in this case, I think we're going to need it. Now, here's the hard part about graphing this. 4.5, if I go up to 4.5, that's right here in the middle. And that part's okay. It's this moving down 1 and over 1 that's the problem. When I move down a whole 1, I end up moving down into half of the next one and then over 1. And I move down to half and then over 1. And I move down to the next half and over 1. Down to the next half and over 1. Down to the next half and over 1. And so you can see my points are now in the middle of these lines, not exactly on a whole number, which is okay. So I connect my line and I extend it with arrows, and this is my first graph. Okay. Now to do my second one, I always like changing a color just to be able to see. You don't have to, this is just a personal preference. Now as I do my second equation, we are going to subtract 2x first. So 4y equals negative 2x plus 13. Make that a plus. Then take rid of the 4, I'm going to divide each number by 4. So I get y equals, now I'm going to reduce my fraction. Negative 2 divided by 4 is negative 1/2 x plus, if we do 13 divided by 4, you end up getting as a decimal 3.25. And this again is the hard one because we're looking at this going, oh boy, this is not part of the way, you know, it's not on a whole number. Okay, but let's go through this. Here's what happens. If I go 3.25, so that's 3 1/4. If I go up 1, 2, 3, and then go a quarter of the way, okay, here's what's going to happen. When I go down 1 and over 2, I got to go down to the next quarter and then over 2. So I'm just below there. And then I'm going to go down to the next quarter and over 2. I'm like right there. And then I go down to the next quarter and over 2. I'm like over here. So I'm going to kind of graph this. And again, you guys are going to be a little bit more accurate because you have your IDs to work with and I don't. But can you kind of see where the intersection is? My lines are not even straight, I apologize. It looks like it's right here, and it looks like it's right at that dot for the blue. Which if I look at this point then, let's see if we can count our way over. 1, 2, 3, so I go over 3, up 1.5. It looks to be about 1.5. Now, the more accurate your graph is, the better your answer ends up being. But what it looks like is that it costs $3 for a sundae and $1.50 for a milkshake. So, as you're going through, what we would ask of you is to say, okay, well, first of all, this system is consistent and independent because it has one solution. And the last thing we would say is it looks like we have $3 for a sundae and $1.50, better write out my dollar, for a milkshake. So as we go through, now what we're going to do in class tomorrow and the next day also is we're going to talk about too how your graphing calculators can do a lot of this work for you. And so if you don't have a graphing calculator, please see me for a calculator contract. You can borrow one for $20, but it is definitely worth in Part B having it right away. So that's the end of the first day of Section 3.1. And what we're going to do when we come in tomorrow is extra practice. We're going to get out some graphing boards and really just kind of work with what do we need to do, how do we solve equations, things like that. But for today, this is all we're asking is that you've watched this, and we're going to work on some homework and practice tomorrow in class.